All right, today we're diving into something really cool called traveler point dynamics. And what it is really is a totally fresh way to look at physics, motion, relativity, even starship travel. Not from some abstract bird's eye view, but from the only perspective that actually matters, your own. I mean, let's be honest, right? We all hear about Einstein and relativity, and it sounds amazing, but when you try to actually get your hands dirty with it, it can feel impossibly complicated. It just seems so disconnected from our day-to-day lives. So what gives? Well, as we're about to find out, a huge part of the problem comes down to how we think about time. You see, traditional physics loves this thing we can call the map view. It's like imagining this giant invisible grid laid over the universe with perfectly synchronized clocks at every single point. But if you're the captain of a starship that's accelerating, or you're anywhere near a black hole, good luck with that. The alternative is what we're calling the traveler's view, which basically says, forget the grid. The only clock that matters is the one on your wrist. It's personal, it feels totally intuitive, and as we're going to see, it's incredibly powerful. So here's our game plan. First, we're going to unpack that whole clock problem with relativity. Then we'll build our very own traveler's toolkit. Once we have that, we'll discover the crucial difference between forces you can feel and forces you can't. We'll even apply it to some awesome starship physics. And finally, see how this all creates a brand new, way more intuitive bridge to understanding Einstein. Okay, so first up, relativity's clock problem. The main issue here is that the old-school map view completely depends on having this huge network of perfectly synced clocks, which is a luxury we just don't have. In the real universe where things are accelerating and gravity is bending space and time just doesn't tick the same everywhere. Relying on a perfectly synced grid, that's like trying to build your house on an earthquake fault line. So to really navigate the universe from our own point of view, we're going to need a different set of tools. And traveler point dynamics gives us 3 simple but super powerful concepts that totally replace that messy, complicated clock network. First up is proper time. This is the bedrock of the entire idea. This isn't some abstract time on a map somewhere. It is the actual, literal time that is ticking by on your personal watch or on your spaceship's main clock. It's the time that you, the traveler, actually experience. And this idea of proper time is so powerful for a few huge reasons. For one, it's frame-invariant, which is just a fancy way of saying that everyone, no matter how fast they're moving, can agree on its measurement. You don't need any outside clocks to figure it out, and it connects the laws of physics directly to your lived experience. In short, it's real in a way that map time just isn't. All right, next in our toolkit is proper velocity. Now, this isn't your everyday miles per hour. It's how much your position on a map changes for every single tick of your own personal clock. This is the key that connects our personal experience of time to our movement through space. So why on earth would we use this? Well, get this. Unlike normal velocity, which famously has a hard speed limit, the speed of light, proper velocity has no upper limit at all. This makes it way more useful because it's directly tied to an object's momentum. If you were actually planning a trip near the speed of light, this is the number you would really care about. And our final tool is proper acceleration. And this one is the most intuitive of all. It's simply the acceleration that you can physically feel. When a rocket fires and you feel that push back into your seat, that is proper acceleration. It's what an accelerometer, like the one that's in your phone right now, actually measures. It's the g-forces. Okay, this next part, this is where it all comes together. We're going to use our new toolkit to understand the real nature of forces, and we're going to do it with a super simple experiment that reveals something profound about how the universe actually works. So, just imagine you're holding your phone, and you've got one of those accelerometer apps running, the kind that measure g-forces, the proper acceleration that the phone is feeling at any given moment. So first, you just hold the phone perfectly still. The app reads 1g. Makes sense, right? Your hand is pushing up against the pull of gravity. But now, for just a split second, you drop it. Just let it fall into your other hand a few inches below. What do you think that accelerometer reads while the phone is in midair? And here is the absolutely mind-bending result. While the phone is falling, the accelerometer reads 0 Gs. Think about that. Even though it's clearly accelerating toward the Earth, from its own perspective, it doesn't feel a thing. Then, of course, when you catch it, you see that big spike as your hand provides a force it can feel. So what is going on here? It's because gravity isn't a proper force that's pushing or pulling on the phone. It's what we call a geometric force. It's a feature of the curved space-time it's moving through. The phone is just following the most natural path it can, and from its perspective, it feels nothing at all. It is, for that moment, completely weightless. And this gives us our huge distinction. Proper forces are what you feel. A rocket engine firing, the floor pushing up on your feet. Geometric forces, like gravity or inertia, are unfelt. They act on every single atom of an object, all at once, equally. And this is exactly why astronauts in orbit are weightless. It's not because there's no gravity. It's because they are in a constant state of freefall around the Earth, feeling zero proper acceleration. All right, enough theory. Let's put this amazing toolkit to the test. We can actually use it to solve problems that sound like they're straight out of science fiction, and we can do it from the intuitive perspective of the captain sitting right there on the starship's bridge. So let's imagine a round trip to a star that's 24 light years away. The ship's going to accelerate at a nice, comfortable 1g for the first half of the trip, then flip over and decelerate for the second half, and it'll do the same thing on the way back. Now let's track the time on two different clocks, one back at mission control on Earth and the proper time clock on the starship itself. For everyone waiting back on Earth, for mission control, for the families and friends left behind, a little over half a century goes by, 53.7 years. An entire generation has passed. But for the travelers on that ship, the ones experiencing their own proper time, for them, only 17.2 years have passed. This isn't some kind of trick. It's a direct result of looking at the physics from their perspective. They aged less than 2 decades, while Earth aged more than 5. And traveler point dynamics makes this seemingly impossible calculation totally straightforward. So this brings us to our final and maybe our most important point. This traveler-centric way of thinking isn't just a neat party trick. It's a fundamentally more intuitive way to get a handle on the physics of our universe. It's like a direct bridge to Einstein's biggest ideas. So, to wrap it all up, physics doesn't have to be this abstract, confusing thing. By just focusing on the traveler's own clock and the forces they can actually feel, we get to sidestep that whole messy synchronized clock problem, we get real clarity on what gravity actually is, and we make these wild concepts like time dilation feel less like magic and more like, well, just good engineering. And that leaves us with one final, really fascinating question. Instead of teaching classical physics first and then having to go back and correct it all with relativity later, what if we started here? What if, from day one, we taught students to think like a traveler, to understand the universe from their own personal point of view? It's a powerful thought to end on. Thanks for tuning in.